Hello, everyone. I'm Mingjun Li from Beihang University. Today, in representation of our group and collaborators, I will present our work, Eventor, an efficient event-based monocular multi-wheel stereo accelerator on FPGA platform. This is the outline. The first part is the research background and our motivation. The multi-wheel stereo, MVS, defines the problem that given a set of photographs of an object or a scene, estimate the most likely 3D shape that explains those photographs under the assumption of known viewpoints. In recent years, a novel bio-inspired vision sensor, event camera, has been exploited as an ideal sensor for MVS systems. Different from traditional frame-based camera, which captures a scene as a synchronous sequence of 2D images. An event camera asynchronously mirror brightness changes on each pixel and output an event stream. It has multiple advantages, which can make MVS systems more efficient and robust. Similar with MVS, the event-based multi-view stereo, EMVS, estimates the subsidence 3D structure from event cameras with known trajectories. Above is a simplified pipeline, and below is a short demo of a typical EMVS system. In our work, we focus on monocular EMVS, which is a critical task in monocular event-based SLAM. EMVS can be deployed in various application scenarios. Benefiting from the low power consumption of event cameras, EMVS is especially competitive when implemented on embedded platforms, such as drones and robots. However, there is no efficient implementation of monocular EMVS on embedded platforms. We review existing works and find out that they all implement EMVS on desktop CPU or GPU, with event processing rate around 1 million per second, which is to say, existing monocular EMVS implementations only run on desktop processors with inadequate performance. And this brings us to the following question. With all the existing MVS accelerators, can we directly use them on EMVS? To answer it, let's compare traditional MVS and EMVS. It can be seen that the data structure and algorithm pipelines are different due to the new paradigm introduced by event cameras. So the answer is no. Previous accelerators for frame-based MVS cannot be directly applied to EMVS. Overall, we can summarize the challenges for deploying monocular EMVS on each devices here. Firstly, EMVS is computational intensive, so the computation speed of the system needs to be fast enough to meet the real-time operation requirement. Secondly, to unlock the potential of EMVS on embedded platforms, we need processors with high energy efficiency instead of desktop processors. Thirdly, due to the new computation paradigm introduced by event cameras, current EMVS algorithms lack hardware-oriented optimization, and previous MVS accelerators are incompatible. These challenges motivate us to improve the performance and energy efficiency of monocular EMVS systems via algorithm hardware co-optimization. In the second part, I'm going to introduce our work, Eventor. To begin with, I'll go through the algorithm framework. Eventor is based on a monocular EMVS algorithm adopting event-based space sweep method. Due to its various advantages, we find it suitable for implementation on embedded platforms. This algorithm first divides the input event stream, event frames, in the event aggregation part. Then it will select key reference view and construct local discretized space volume, which is called DSI. In the event back projection part, events in the event frame are back projected to the reference viewing space. And the volumetric recounting part counts the number of back projection rays that pass through each DSI voxel. If the input event frame is selected as keyframe, the local scene structure will be detected by finding local maxima of the rate density in DSI. And then the depth information will be converted to point cloud and merged into the global map. We do software runtime profiling on Davis event camera dataset and simulator. The result shows that the event back projection and volumetric recounting tasks are the bottleneck of Emvs algorithm. Therefore, we accelerate these two tasks on FPGA to achieve the best implementation results. Based on the profiling results, we optimize the software framework to make it more hardware friendly. To begin with, we need to define some critical tasks. The process of event back projection and volumetric recounting can be divided to several subtasks. Event back projection is executed in a two-step manner: the canonical event back projection and the proportional event back projection. Most of the computation workloads lie in these two tasks and the whole volumetric recounting task. The first optimization approach is algorithm reschedule. We partially reschedule two tasks: event distortion correction and compute proportional back projection parameters. This strategy can effectively improve the memory access efficiency and reduce data transfer. After reschedule, the computational intensive stages are compacted for pipeline acceleration. The second optimization approach is approximate computing. When counting the number of back projection rays that go through each DSI voxel, there are two voting strategies. Among them, nearest voting has lower computation complexity and more hardware-friendly memory access pattern. Through our evaluation on Davis dataset, nearest voting only got slightly higher reconstruction error compared with bilinear voting. Therefore, we adopt nearest voting as an approximating strategy in volumetric recounting task. And the third optimization approach is hybrid data quantization. Most data involved in Emvs data flow are represented by floating point format. We convert them as fixed point formats. For event coordinates in different projection stages, we adopt a hybrid quantization strategy to guarantee the accuracy. The parameters and DSI scores are also quantized. In this way, up to 50% memory requirement and data transfer bandwidth are saved. The computational logic on FPGA is also simplified. Through our evaluation, the reconstruction error before and after quantization has quite little difference, which shows that the accuracy of the quantized framework is acceptable. Based on our optimized Emvs framework, we design and implement the hardware part of Eventor. To effectively accelerate Emvs using customized hardware, we need to fully utilize the computation parallelism. The parallelism of Emvs can be divided to three levels from fine-grained to coarse-grained. The first level is operator level. Multiple ALUs can be deployed to accelerate matrix and vector computation. The second level is event level. Different events can be processed in parallel, and the process can be pipelined. The third level is DSI level. Executions related to different DSI voxels can be executed simultaneously. We use these three levels of parallelism to get the Eventor architecture design. Here's the overall architecture of Eventor. Eventor is an ARM FPGA heterogeneous accelerator. When it starts working, the ARM CPU configures DMA to transfer input data from DRAM to input buffers on FPGA. Then it fires up the acceleration modules on FPGA, which receive input events and update DSI data stored in DRAM. There are two acceleration modules on FPGA. The canonical projection module, which executes the canonical event back projection task, and the proportional projection module, which executes the proportional event back projection task and the volumetric recounting task. The canonical projection module has input buffers and intermediate buffer realized by the manner of double buffering, which guarantees continuous loading and streaming output. the computation inside the module is done by the process element, PEZ0. It is composed of matrix vector MAC units and a normalization function unit. The whole module is controlled by a finite state machine controller. For the canonical projection module, multiple ALUs are deployed to accelerate matrix and vector calculation, which exploits operator-level parallelism. Input events are processed in a fully pipelined scheme without data dependency, which exploits event-level parallelism. Next is the proportional projection module. A specially designed data allocator fetches input data and allocates them to process elements. Multiple PEZI composed of scalar MAC units, nearest voxel finder, and volt address generator are responsible for parallel computation. The output buffer is also realized by the manner of double buffering, and the volt execute unit uses the volt addresses stored in the buffer to update DSI scores in DRAM. The whole module is also controlled by a finite state machine component. For the proportional projection module, besides exploiting operator-level and event-level parallelism in the similar way of the previous module, it additionally exploits the DSI-level parallelism by deploying multiple PEs to simultaneously back-project an event to multiple DSI voxels. As for the workflow of two FPGA acceleration modules, we adopt a parallelizing mechanism to improve the throughput. This image shows the unparalleled pipeline. As you can see, there is a lot of idle time. In our pipeline workflow, for normal event frames, Eventor decouples the execution of two modules. In this way, they work simultaneously in a pipeline manner, and the execution time of canonical event back projection is overlapped. This pipeline workflow exploits the event-level parallelism. Now, let's see the evaluation of Eventor. In our experiments, we implement Eventor on Xilinx Zinc SoC and evaluate on Davis event camera dataset and simulator. Both simulated and real scene sequences are used for testing. The original Emvs implementation on Intel i5 CPU is selected as the comparison baseline. Here's the resources utilization of Eventor. It can be seen that Eventor uses quite few resources. We first evaluate the accuracy of our hardware-friendly Emvs framework. The figure shows the comparison of average depth estimation error between the original Emvs and our reformulated framework. We can see that the maximum difference is only 1.78%. In some sequences, our framework even has better accuracy. On the right side, a sample of reconstructed scene structure from simulation 3 planes sequence is presented for direct demonstration. Overall, the results indicate that the accuracy of our reformulated framework is comparable to original Emvs. Then we evaluate the performance of Eventor. This table shows the performance comparison between Eventor and original Emvs run on Intel i5 CPU, including the runtime, the event processing rate, and the power consumption. Compared with Intel i5 CPU, the event processing rate of Eventor is just slightly higher. However, in terms of power consumption, Eventor shows great advantage. So, for the energy efficiency of the entire system, Eventor can achieve up to 24 times improvement compared with desktop CPU. At last, here's a summary of our work. In conclusion, we propose an efficient Emvs accelerator Eventor for real-time applications and evaluated on Zinc FPGA platform. Algorithm hardware co-optimization strategies are utilized to improve the system's performance. As a result, Eventor could achieve 24 times improvement in energy efficiency compared with Intel i5 CPU. The overall performance could satisfy the requirements of real-time reconstruction on power-limited embedded platforms. That's all for my presentation. Thank you for listening.